We're Group 2, and we're here to talk about DDPG and TD3. To talk about the background of this paper, it is best to look through the timeline for evolution of control. First, we have DQN. It cracks stable deep value learning by introducing two key ideas, experience replay and a separate target network, and showed you can learn straight from pixels and Atari games. But DQN assumes discrete actions. In continuous control, take the argmax over actions becomes a hard inner optimization every step, which isn't practical. And if you try to discretize, the action count explodes and you still lose the smoothness you need. That's the pressure pushing beyond DQN. Then we have DPG. Deterministic policy gradients say don't search over actions, learn a deterministic actor, and update it by backpropagating to the critic. Crucially, you can do this off policy, reusing data collected by a different behavior policy, great for data efficiency. Early neural variants, though, were brittle or relied on batch learning, which doesn't scale to large networks or online updates. That sets the stage for the next step. We have DDPG and TD3, which we'll cover mainly further in our presentation. To give you guys a brief overview, DDPG is a fusion. It takes DPG and import DQN stabilizers. And TD3, since people noticed DDPG runs could still be brittle, they stepped back and created a result that behaved more reliably on Mujoko benchmarks. We'll get into the mechanics soon. Here's a quick refresher. Q-learning learns a Q function and picks actions with an argmax. It's great for discrete actions. Actor-critic splits roles. The actor proposes action, the critic scores them, and the actor climbs the critic's gradient. In off-policy learning, we can train from data gathered by another behavior policy, so we can reuse a replay buffer, whereas on-policy needs fresh data for the current policy. Replay plus target networks are the classic stability combo that DDPG adopts. Importantly, both DDPG and TD3 are model-free. They don't learn or use a dynamics model, so sample reuse is crucial, and comparisons to model-based planners frame their impact. Finally, overestimation bias. It maximizes noisy Q, setups Y, TD3 adds its fixes later. The paper frames four concrete obstacles. First, continuous actions. The DQN argmax becomes a full optimization every step, and if you discretize, the action count explodes, and we lose precision. Second, deep value learning with bootstrapping is fragile. When the same network defines both the target and the update, TD can diverge with large nonlinear approximators. Third, exploration itself is non-trivial in continuous spaces, particularly for systems with inertia. Finally, we want this to work not only from low-dim states, but also from pixels. DQN nailed pixels, but not continuous actions, so this gap is squarely in scope. This problem is important because robots need smooth, continuous torques, not bins, and real interaction data is expensive. Off-policy replay decouples exploration from learning so we can aggressively reuse experiences. The payoff the authors are after is generality with simplicity, which is one lean actor critic that works across a slate of physics tasks from joint angle states to raw pixels. Historically, DPG suggested the right direction but didn't scale. DDPG specifically addresses that scaling gap by combining off-policy actor critic with stability tricks proved in DQN.
Moving forward, let's discuss about DDPG algorithm and its significance. So, deep deterministic policy gradient is a model-free off-policy actor-critic algorithm for continuous control that learns a deterministic policy guided by a critic. It stabilizes learning with a replay buffer, target networks, and action noise for exploration. Before moving to algorithm, the different components of DDPG are a deterministic actor, a critic, copies of actor and critic, which we call them as target networks, a replay buffer for storing off policy transactions, and exploration noise. One thing that I want to emphasize here is the Q learning equation, which is slightly different from the one that we have seen in the class. So in the class, there is an expectation term here with QUST plus 1. Because we are trying to determine a deterministic policy, we can remove that term from the equation. Now let's dive into the DDPG algorithm. In the first step, from with the initial state, the actor tries to determine an action. We normally add some noise to the action for exploration. Then we store the transactions in the replay buffer. And periodically, we sample transactions from the replay buffer and we pass it on to the critic. We get target labels from the slow copies of actor and critic because directly taking the values from the models which are changing during the training can cause instability in training. So slow copies make bootstrap targets stable, preventing those feedback loops. And using those target values, we minimize the mean squared loss between the q value predicted by the critic, and we update the critic and we send the gradient along with the advantage to the actor. We update the actor to increase the critic score, and so this basically directly nudges the actions towards higher value actions. And after we update the critic and actor, we do a soft update on the copies of actor and critic. uh, we update by using this weighted equation so that they do not diverge significantly from their initial state, and it keeps the learning smooth. So some important insights from DDPG algorithm are, so it was the first algorithm that had deep Q learning. So they wanted to stabilize learning on neural networks. The ideas that they used here were off policy algorithm. They could use batch training by having stored different transactions in the buffer. Then the second thing, they use soft target updates using the copies of actor and critic. It's kind of a slow learning, but it avoids the instability in training. The third thing that they used was batch normalization. It helped stabilize the learning when observations had multiple continuous features on different scales. Although we see batch normalization is a very common technique these days, it was a very new method back in 2016 when DDPG was discovered. And they also added noise in the state input. Because the policy is deterministic, we want it to still explore. We don't want the actor to stuck in a single path.
We now describe the experimental setup of the DDPG paper, which was evaluated on a wide variety of simulated environments, mostly built in Mujoko and Torx. Mujoko provides realistic physics for robotic control tasks, while Torx is a car driving simulator for steering and acceleration control. These environments fall into a few main categories. First is classic control problems, which are simple tests of balance and stability. Locomotion tasks, which require coordinating multiple joints for forward movement. And manipulation tasks, where the agent must interact with objects, grasp, lift, or move them to a target. There are also task variants such as serial and parallel cart pulls designed to test the algorithm's robustness. DDPG was trained on both low-dimensional state inputs and high-dimensional pixel inputs. Overall, this diversity of environment showed that DDPG could generalize across different types of continuous control problems. So the DDPG paper was groundbreaking because it was the first deep reinforcement learning algorithm that successfully handled continuous action spaces. It solved over 20 different physics-based tasks mentioned before using the same hyperparameters and network architecture across all tasks. Even more impressively, the policies it learned were often competitive with model-based planning algorithms that had full access to these simulators' underlying dynamics, something DDPG never sees. So the main takeaway is that DDPG demonstrated for the first time that deep actor-critic methods can scale to high-dimensional continuous control, bridging the gap between discrete DQN style methods and continuous robotic control. Despite its success, DDPG also has limitations that later algorithms tried to address. The first issue is overestimation bias. Because the critic is trained with bootstrap targets, small errors in the Q function tend to accumulate, leading to a systematic overestimation of value estimates. This can make training unstable and cause the actor to exploit these overestimated Q values. Second, DDPG suffers from high variance and error accumulation. Temporal difference learning propagates noise through the updates. And since the actor directly depends on the critic's inputs, any critic error feeds back into the policy updates, reinforcing bad behaviors. Finally, the deterministic nature of the policy can lead to policy overfitting. Now that we've seen the challenges with DDPG, how do we overcome them? Well, to reduce overestimation bias, one idea is to train two critics instead of one, and when computing the target value, take the minimum of the two. This conservative estimate prevents the actor from exploiting inflated value predictions. Next, to reduce error propagation, we can delay actor updates. That is, let the critics learn for a few steps before updating the actor. This gives the critics time to stabilize so the actor isn't chasing a moving noisy target. Finally, to prevent overfitting to noisy Q values, we could use target policy smoothing by adding a small amount of clip noise to the target actions. This discourages the actor from overreacting to small fluctuations in the Q function and promotes smoother, more stable policies. And then we combine all these refinements together and we arrive to the twin delayed deep deterministic policy gradient, or TD3. It is essentially DDPG but made robust, stable, and reliable for high dimensional continuous control tasks.
I will now walk you through how these show up structurally and why they help stabilize training. This diagram shows how TD3 modifies the DDPG architecture. You can see that instead of one critic, we now have two, both trained on the same experience. During target computation, we take the minimum of the predicted Q values to prevent overestimation. The target actor adds clipped Gaussian noise before feeding the action to the target critics. This is the target policy smoothing step that helps regularize learning. Then we have the delayed actor update. The actor is only updated after the critics have been updated for a couple of steps, so its gradient is based on more stable value estimates. Finally, the soft updates still keep all the target networks slowly tracking the main ones. In the equation on the left, R is the reward, gamma is the discount factor, S dash is the next state, and A tilde dash is the next action, which is a noisy version of the action from the target actor. Phi 1 dash and phi 2 dash are the parameters of the two target critic networks. The experimental setup for TD3 is the same as that of DDPG. Implementation-wise, TD3 is model-free and off-policy just like DDPG, but it introduces a key hyperparameter, policy delay factor, controlling how often the actor updates related to the critics. Results are usually compared against DDPG, PPO, TRPO, and SAC to measure both stability and sample efficiency. This table captures the essence of what TD3 fixes compared to DDPG. The biggest issue in DDPG was overestimation bias. Critics would inflate Q values, leading to unstable learning. TD3 solves this with two critics and a minimum operator for conservative targets. Next is error accumulation. In DDPG, the actor updated too fast on noisy Q values. TD3 delays actor updates, giving critics time to stabilize. Then there's policy overfitting, where deterministic policies latch onto spiky Q functions. TD3 adds target policy smoothing to regularize that surface. Altogether, these changes make training more stable, more robust, and far less sensitive to the hyperparameters. Even though TD3 performs very well on benchmark tasks, it's not perfect. It can still converge slowly and struggle with exploration, especially in high-dimensional or sparse reward environments. There's also the issue of computational costs. Training two critics and handling delayed updates can make the algorithm heavier, which becomes noticeable in robotic applications. In some complex control tasks, TD3 might get stuck near boundary actions or suboptimal strategies due to limited exploration. So, while it improves stability, there's still room to make learning faster and exploration more efficient. Many extensions build on DDPG and TD3's actor critic code to improve stability, data efficiency, and exploration. Methods like D4PG and randomized ensemble double Q use richer value targets and multi-step returns for faster, more stable credit assignment. Techniques such as HER and DDPGD make training more feasible when rewards are infrequent by relabeling goals or using expert demonstrations. Approaches like parameter space noise and GEP-DDPG promote more consistent, goal-driven exploration rather than random action noise. Recurrent DDPG adds memory through recurrent networks, while multi-agent DDPG uses centralized critics to coordinate multiple agents. Algorithms like Daydreamer learn a world model for imagined rollouts, improving sample efficiency and planning. Overall, these directions extend DDPG's foundation to handle more complex realistic settings. That brings us to the end of our presentation. Thank you so much for watching.